Hello, my name is Marcin Jurdziński, and I work at the University of Warwick. In this tutorial, I want to give you a gentle introduction to games. Now, game theory has been forged in the famous 1944 monograph by John von Neumann, mathematician, and Oskar Morgenstern, an economist. And their goal was to develop a mathematical theory to reason about economic behavior. And indeed, the title of the book itself is The Theory of Games and Economic Behavior. Now, that project has arguably been rather successful. Game theory as a language, as a set of methodologies, is by now used as standard in many social sciences, but also in some natural sciences. So one example is evolutionary biology. In the last 20-30 years, game theory has had quite a vibrant and successful interaction with computer science as well. That led to the development of areas such as algorithmic game theory or algorithmic mechanism design that have their own dedicated conferences and quite a lot of impact, including in industry, but also in areas such as complexity theory, where characterizing the computational complexity of certain game theoretic problems and questions has stimulated creation, invention of new complexity classes and new computational hardness phenomena. However, in this tutorial, all or most of this goodness is not ready for us. Instead, because it's a tutorial for the Theoretical Foundations of Computer Systems program at Simons, I'm going to focus on games that arise from logic and automata and are in a sense outside of the mainstream of modern algorithmic game theory. Nevertheless, the motivations and applications to logic, automata, and then also to verification and synthesis are algorithmic. And indeed, in this tutorial, my focus, the technical focus, is going to be on algorithmic questions. In a sense, this tutorial is going to be narrower than most of the other ones, if not all of the other ones, in that we are going to focus in particular on one model called parity games. Now, I hope this will still be useful for to some or maybe even many of you, given that parity games, in fact, the computational complexity of parity games ought to be even more specific. The question whether there is a polynomial time algorithm to solve parity games is an open question, has been open for quite a while, and it's very accessible. I strongly believe that there isn't much that anyone needs to learn in order to start engaging with the problem meaningfully. So hopefully in this program we will find opportunities for doing so. But before I tell you about games on graphs and parity games in particular, let's ask ourselves why games on graphs? What are the reasons why games on graphs are interesting? And I'm going to showcase a few classic problems in automata theory, logic, and their applications to verification and synthesis, where games on graphs, and in particular parity games, arise. We're going to start with an application to tree automata complementation. It's a classic result of Rabin that has been already mentioned in tutorials by Mikołaj and Orna. And my goal here will be to actually give you a fairly rigorous, detailed proof of determinacy of party games, which is one of the key technical tools that are used in the proof of the difficult proof of Rabin's result that tree automata can be effectively complemented. But before we go there, let me give you a very primitive, in a way, very simple, very general model of games that we are going to consider in this tutorial. So games on graphs that we are going to consider are played by two players. For now, let's call them 1 and 2, player 1 and player 2, although very soon we are going to give them various names depending on context. These two players play on a graph, and what they do is that they interact in a very simple way. Namely, they pick edges, and who picks the next edge to follow depends on who is the owner of the current vertex. So the vertices in this graph often will be referred to as positions. The edges in our graph will often be referred to as moves, and we have a partition of the set of vertices into those that are owned by player 1 and those that are owned by player 2. So that's one part of the specification of the game, which describes what the arena, so to say, on which the game is played, and what the rules of movement are in the game. Now there is the other component, which in this very general formulation is simply a set of infinite paths in the graph. And you should think of this set as a referee. Once players complete their infinite interaction, in which they jointly pick an infinite path, that set, the referee, so to say, will determine who the winner is. Indeed, we will say that player 1 wins an infinite path in our graph G if and only if that infinite path is a member of set W1. Otherwise, it will be player 2 who is the winner of such a path. And now, how do players form such a path? Let's be very specific. They start in some vertex, some dedicated vertex, let's call it V0, and then whenever the current vertex, and it's the current vertex at the beginning, and then whenever current vertex Vi belongs to the set of vertices owned by player 1 or 2, so the owner of the vertex moves to another vertex which happens to be connected by a directed edge from the current vertex, and then the next vertex becomes the current vertex. So that's how players interact in order to form an infinite path. So this model is very basic, very primitive in a way, and I told you that we will often focus in this tutorial on party games, so let me tell you what a party game is. So here is an example of a party game which is played on this finite graph with 4 vertices, and what we often refer to as the winning condition, that set of infinite paths that are winning for one of the two players, here is going to be represented in a special way. It's going to be represented by this function which labels every vertex by a positive integer in some range from 1 to d. So every vertex is labeled by an orange number, and we call the number of each of those vertices its priority. So this is a bit of jargon that is used in parity games. Now, why parity games? In a parity game, we have 2 players. We will call them even and odd. In the pictures that I draw, I typically represent vertices owned by even by squares. Now, it's easy to remember because squares have 4 sides and 4 is even. And I will tend to represent or draw vertices or positions owned by player odd, either by triangles or maybe pentagons, if triangles are too hard to draw, but both pentagons and triangles have three sides, and hence it's easy to note that they belong to player odd. So this is a party game. Now, I will often refer to, because we are interested in algorithms, I will often refer to the size of a parity game if it is a finite parity game, in the sense that it's on a finite graph. I will often denote it by n and try to keep it blue on the slides as much as possible. So we know how parity games are played because they are games on graphs, and games on graphs in this tutorial always get played in the same way. We start at a certain vertex, and then the owner of that vertex, in this case even, because we have a square, picks one of the outgoing edges. There are two, either the self loop or this one, and in this illustration we always choose the fat edges, or the players choose the fat edges, and hence the resulting play here, this edge is chosen by even, then this edge is chosen by odd, and then this edge is chosen by odd, this edge, that edge, and forever the two players interact to form a path which consists of the prefix and infinite repetition of this tree cycle. Now, how is this labeling by priorities determining the winner? How does the arbiter work here? Well, here's the definition. We will say that even wins a sequence of vertices. So in other words, the sequence of vertices belongs to the winning set of winning plays for even, if and only if. And that's a really, if you see it for the first time, it may seem really ad hoc. Here's the condition. The condition says that the highest priority that occurs infinitely often, or in other words, the lim sup of the priorities of all vertices that occur in that infinite play, is an even number. Now, it does exist because there are only finitely many integers. Even if the graph itself was infinite, in the parity games that we consider here, we only allow a finite number of priorities. So that number certainly exists, and if it is even, then even wins. If it is odd, then odd wins. Now, I will not blame you if you find this definition crazy and ad hoc, but I hope to convince you that it is not as frivolous as it seems, and in fact it really plays a very central role in the applications of automata in logic that you have, for example, seen in Mikołaj's tutorial, and indeed as discussed by Orna in her tutorial on automata. Our first motivating example of the uses of games on graphs, and parity games in particular, is the famous result of Rabin that satisfiability for the monadic second-order logic on infinite trees is decidable. So this is one of those first and very influential examples of the use of the automata method that Mikołaj's tutorial is about, for showing decidability of logics. The technical core of Rabin's solution of this problem is a proof that automata on infinite trees, non-deterministic automata on infinite trees, can be effectively complemented. Or in other words, that there is an algorithm that, given an automaton on trees, produces another automaton that recognizes all the trees that are not accepted by the original automaton. Now, as Mikołaj has pointed out, this is a complex and subtle proof. But by now it has been digested by many generations of researchers because the techniques in Rabin's proof were so fruitful to study other problems. And by now we have proofs that are fairly well streamlined, conceptually clean and elegant, teachable, and many of those have two main technical ingredients or components. One of them, and both of those are non-trivial results. One of them is determinization of automata on infinite words. That's something that you will have learned from Orna's tutorial, and this is indeed a highly non-trivial topic with several solutions and ongoing research on making this algorithmically feasible. The second component is positional determinacy of games, and in the modern treatments of the proof of Rabin's theorem, the specific games for which we want determinacy, and in fact positional determinacy, which I will explain soon, are indeed parity games. But first of all, what is the game? So imagine that we have a tree automaton A. Now a tree automaton has a set of states, an input alphabet. It has an acceptance criterion or an acceptance condition, which, like games that we have introduced, can be thought of as a subset of sequences, infinite sequences. In this case, it's subset of infinite sequences of states of the automaton. And of course, in order for the automaton to be finite, we want some finite array representations, and one of them is indeed assigning priorities to states of the automaton and using the parity condition. Whenever we want to define acceptance of a structure, like in this case the binary tree by an automaton, typically we define a concept of a run. But this is a tutorial about games, so let me give you an alternative and equivalent definition in terms of what sometimes is called the acceptance game. So here's an acceptance game for a tree automaton A, a non-deterministic tree automaton A. By the way, there is an initial state missing here, so there should be either an initial state or a set of initial states. But we have an acceptance game on an automaton and a specific tree, where the tree is understood as a labeling with letters from some alphabet sigma, of that alphabet sigma, of all the nodes in the tree, which in the case of the complete binary tree are simply sequences, finite sequences of zeros and ones. So what is the game? What is the acceptance game, which will determine whether a tree is accepted by the tree T is accepted by the automaton A or not? In this game there are two players. We call one automaton and the other the pathfinder. And the intuition here is that the automaton aims to show that the tree is in the language of the automaton. Or in other words, the task of the automaton will be to build, to construct, or to prove that they can successfully construct an accepting run of the automaton. On the other hand, the task of the pathfinder is to try to disprove that, try to show that the tree T in fact is not in the language accepted by the automaton A. So the task of the pathfinder here would be to prove, to provide evidence that there is no accepting run of the automaton A on tree T. So we are going to capture this condition instead game theoretically. So we have two players, the automaton and the pathfinder, but what are the positions and moves, and then what is the winning condition? Well, the positions are going to be of two types. They will be either pairs, a node in the tree, so a node is always a finite sequence of zeros and ones, and a state of the automaton. And the other type of nodes will consist of other type of positions will consist of a node again and a pair of states. Now, it will be the automaton who owns and hence moves, picks an outgoing edge from positions of the form node state, and it will be the pathfinder who will make moves in positions of the form node and a pair of states. Now the intuition here is that the automaton is in fact going to pick transitions. So if the automaton is at the node n of the tree, so here we have an illustration of a tree, and the current state in the run that the automaton is trying to construct is q, then the automaton can pick out of all the possible transitions from state q, and upon reading letter t of n, which is exactly the label of node n, each of those transitions gives a pair of states. And the intuition here is that these pairs of states denote the states that, according to this transition, non-deterministic transition, are going to be sent to the left and the right children of node n. Now, it's a game rather than doing both, as we would in the concept of a run. We let the opponent, the pathfinder, to pick which direction they want to move in. In other words, what the automaton needs to do is to demonstrate that they can continue successful runs from both q0 in the left child of n and q1 in the right child of n. Now the pathfinder is going to have a choice of either going to the left by proceeding to node n concatenated with 0, or to the node n concatenated with 1, and then from there try to disprove the claim by the automaton that they can construct a run starting from respectively state q0 and q1. But what does it mean for a player to strive or to aim to achieve something? Well, we are going to formalize it using the concept of a winning strategy. So what is a winning strategy? In a game on a graph, like the games we are considering here, it will be a function, sigma, which for any finite sequence of vertices, the last of which belongs to that player I, gives us another vertex. Now, of course, it needs to be a valid move. So what must be the case in order for such a function to be a strategy is that if strategy sigma yields vertex w or position w on this prefix or history of the play so far, which ends with vertex or position vk, then vkw is an edge in the graph. So in other words, the strategy provides valid moves. Now, if you think about it and take two strategies, say sigma 1 and sigma 2, one for player 1 and the other for player 2, and if you start in some initial vertex v, or v0, and each of the players follows their strategy, either sigma 1 or sigma 2, in this sense, then it should be quite clear that what's going to happen is that that will uniquely determine the infinite path starting at that vertex v, and that follows those two strategies, sigma 1 and sigma 2. Okay? So with this concept of a path determined by complete description of what each of the two players are doing according to their strategy sigma 1 and sigma 2, we can now define what it means for a strategy for one of the players, say strategy sigma 1 for player 1, to be a winning strategy for her from some initial vertex v. So it will be the case if if for every strategy sigma 2 of player 2, so in other words, no matter how player 2 behaves, it is always going to be the case that the unique path that is obtained by starting at V and then following sigma 1 and sigma 2 is a win for player 1. So now with the rigorous definition of winning strategy in a game, we are ready to define what it's when a tree is accepted by an automaton A. Firstly, let's clarify that an infinite path in this acceptance game, in which we alternate between positions of the form node state and node pair of states, is winning for the automaton if it is the case that the sequence of states that occur in these positions of the form node state and ignoring the positions node pair of states. So if the sequence in the second coordinates of the automaton states is a sequence in this acceptance condition of the automaton. So now we can say that the automaton A accepts tree T if and only if a player automaton has a winning strategy starting from the node of the tree, which is its root, and from one of the initial states. Right, so let's maybe try to understand better the concept of a winning strategy, and in particular the concept of a winning strategy for even in a parity game. So here's an example of a parity game with 10 vertices, 10 positions, and 6 distinct priorities from 1 to 6. And perhaps it may take a bit of time for you to figure out whether even has a winning strategy in this game or not, and if so, from which vertices is the answer yes, and from which vertices is the answer no. I'd like to now help you and convince you that in fact, even in this parity game with 10 vertices, 10 positions, has a winning strategy from every starting vertex. And indeed, the strategy of player even in this game is of a very simple form. It's a very important, very useful concept. It's a positional strategy. What does it mean for a strategy to be positional? Well, it means that in this strategy, the move that is picked by the player, which is an outgoing edge from the current vertex, is completely independent of how we have arrived to that vertex, what the history of the play so far is, where it has started, which vertices it has visited, in what order, and how many times. All of this is irrelevant. When you arrive at a vertex, a positional strategy will always tell you to follow the same edge. So here's an example of a positional strategy, which by the way can be formalized as a function from positions owned by even to set of vertices. In this parity game we have 4 different vertices that belong to even. They are the squares. All the others are triangles, and hence they belong to odd. And the edges that are dictated by a positional strategy, the green positional strategy here, are simply the green edges. So now I'd like to convince you that this positional strategy is winning for even in this parity game. And the way to do it is to do the following very simple mental exercise. Simply ignore all the edges that player even will never use. They are the thin edges. This one, and this one, and this one. So let's just throw them out. And indeed, let's also forget which vertices are vertices of player even and which vertices are where player odd moves. Let's just ignore that, because from now on every edge is possible, right? We have committed to a single outgoing edge from every square, but the opponent can do whatever they damn please and whenever they want to do that. So all edges are in place. So let's keep all the edges outgoing from positions owned by odd, but let's only include the green edges that were picked in that positional strategy for player even. So what we now have is what I call the strategy graph. Right? So the strategy graph is the one without the thin edges. It's only the outgoing green edges and of course all the outgoing edges for the opponent. And I hope that if you stare at this graph, much shorter than before, you will convince yourself that every cycle in this finite graph is even, and from that it's an easy exercise to conclude that every path in this finite graph with priorities on vertices has the property that the highest priority that occurs infinitely many times is even. And indeed, in this example, somehow the principle of movement is that you either go left or you go up, and whenever you go up, you go to a vertex with a very high even priority, higher than what you've seen recently. Okay, so that's a very useful picture to keep in mind. It will underpin one of the key concepts of an attractor decomposition that we are going to study in this tutorial. Now let's talk about determinacy. We say that a game is determined from a vertex V if it is the case that at least one of the two players has a winning strategy. Right? So here we have a statement that there is a strategy for player 1 such that for every strategy of player 2, the unique play that results from following those two strategies starting at vertex V is a win for player 1. And here's an equivalent, an analogous statement about existence of a winning strategy for player 2 from that same starting vertex V. And if this dichotomy holds, then we would say the game is determined from vertex V. And then we would say that the game is determined if it is determined from every starting vertex. Now, it is very tempting to think that clearly if one player cannot win, the other must be able to. Well, indeed, this intuition is not that wrong, because this dichotomy holds for all finite games and holds quite naturally. There is a standard, very natural procedure sometimes called backwards induction, which allows you to show that every finite game in which every play results in a win or a loss, or a win for one of the players, is determined in the sense of this dichotomy holding. That's why we know that if you exclude, by tweaking the rules, if you exclude draws in, say, chess, either black or white have a winning strategy. We just don't know which one that is, because the game is just too large. But it's finite, so in this sense, it's really trivial. It's determined because all finite games of perfect information, let's not go into technical details here, is determined. On the other hand, with infinite games, things get tricky, and indeed, there are non-determined games. For example, using the axiom of choice, one can construct one. There are some funky constructions of non-determined games. Let's not go there here, but it's useful to keep that in mind as a cautionary matter. So This issue of when games are determined has been studied, and has been studied by set theorists, in fact. Gale and Stewart have been first to pose the question of whether games are determined depending on their topological complexity, or rather on the topological complexity of the winning sets. So here is a natural topology on the set of infinite sequences of positions, or on infinite paths in the game graph. So the basic open sets are defined to be the cylinders, which are simply the sets of all infinite paths which have the same prefix pi. So we have a cylinder for every finite prefix pi. And then the open sets are simply unions of all of basic open sets. And a natural hierarchy of sets of increasing complexity is the so-called Borel sets, which sort of at the bottom of the hierarchy have open sets, and we say that the set is Borel if it is if it can be obtained from open sets by two kinds of operations, either complementation or countable unions. Now note that if you have countable unions and complementation, then you also have countable intersections. This is a subtle, right? So the construction of Borel sets is quite subtle, and it's in particular it's not true that there are only finite levels of Borel sets, because we have countable unions, so we can do some kind of diagonalization and go beyond all the finite levels, or levels that result from just finite number of applications of a complementation or a countable union. So it's quite it's a very rich family of sets. And it was Gale and Stewart who have shown early in 1950s that, and that proof is not difficult, that every open game is determined. Right? So every game in which the winning condition, the winning criterion, is an open set is determined. It's a bit harder than doing it for clopen sets, because games with clopen winning sets are essentially equivalent to finite games. But they pose the question whether you can climb the Borel hierarchy. And it was Marcin, in a rather complex and impressive result, who has shown that every game with a Borel winning condition is determined. So that's a very powerful result. Sometimes can be useful as a big hammer if you want to establish whether some tricky game that you're considering is determined or not. You could use Martin's theorem. So I have an exercise for you. Prove that the set of sequences or paths that are winning with respect to the parity condition, namely that the highest priority that occurs infinitely many times is even, is indeed a Borel set. So it's if you are not familiar with Borel hierarchy and Borel sets, it's a useful exercise. But wait a minute. Why did we start talking about party games at all? Well, here is one answer. In 1966, McNaughton has proved this very influential result, that every non-deterministic Bihi word automaton can be determinized. So there is another equivalent deterministic word automaton. However, deterministic Bihi automata are less expressive than non-deterministic Bihi automata. So this result cannot possibly hold for deterministic Bihi automata. So what are the alternatives? And in fact, MacNaughton used Automata with an acceptance condition called a Mala condition. Then later Safra has significantly improved the complexity of MacNaughton's construction, which was very influential and uh, led to lots of work, which I will mention later. But and and Safra used another acceptance condition called Rabin condition. But nowadays there are constructions, including those by Peterman, later by Sheva and others, that yield directly a parity automata. And parity automata have various benefits, one of which is that parity games are positionally determined. And that turns out to be particularly convenient technically in various contexts. So this result of Emerson and Jatla from early 1990s, that every parity game is positionally determined, that is, from every starting vertex, one of the two players has a positional winning strategy, turns out to make working with parity automata particularly convenient. So finally, let's see just a sketch of the construction in this hard part of Rabin's result, which is the complementation of tree automata. So we defined acceptance of a tree by an automaton using a game in which we had two players called automaton and pathfinder. And we defined tree T being accepted by an automaton, or in other words, belonging to the language accepted by the automaton, if it was the automaton player who had a winning strategy. Now, if we want to construct an automaton that accepts exactly all those trees that are not accepted by A, then we can use determinacy to conclude that we want to accept exactly all those trees for which the acceptance game, the game based on the automaton and the tree, is such that Pathfinder has a positional winning strategy in that acceptance game. Right? Because by determinacy we know that if automaton doesn't have a winning strategy, then Pathfinder does. And one way to provide a modern proof of this difficult result by Rabin is to construct an automaton, let's call it A bar, in such a way that what it's going to do is that it's going to guess, that's where we use non-determinism, and then verify in parallel, simultaneously verify a whole positional winning strategy for Pathfinder in the acceptance game. Right? So this automaton, A bar, will be able to accept a tree if and only if it is capable of guessing and verifying, confirming that a strategy that it has guessed, a strategy for Pathfinder, is indeed winning for Pathfinder, and hence it is impossible for the automaton to accept that tree, because otherwise it would be the opponent who has a winning strategy, and that's impossible. So now this process of guessing and verifying a whole winning strategy for Pathfinder is quite subtle, and both determinization of word automata and determinacy of games, and in fact crucially what is sometimes referred to as forgetful or finite memory determinacy, but if we are lucky enough to have the parity acceptance condition, in fact you don't need memory at all, positional strategies are memoryless. Those two components allow this subtle process to succeed. They allow for this verification of, for guessing and the verification of the guessed strategy for Pathfinder to be done using a finite automata non-trees. So we will not go into all the gory details of that, but I think it's very useful to be aware of the importance of positional determinacy and of determinization of automata on words when we want to complement automata on infinite trees. And thanks to the result of McNaughton, Safra, and their followers, all we need to consider is acceptance games with parity conditions